Okay, so in this next section, what we're going to do is we're going to start to learn to name an alkane. And we're going to learn how to name an alkane given its structure, and we're going to learn how to draw an alkane given its name. What I'm about to embark upon is going to be the foundation that we will build upon in future chapters when we start adding functional groups. So you need to understand this process. Again, I plan to spend a significant amount of time in class working problems. So you may want to save some space after this, after the descriptions that I'm going to use. But I'm going to spend some time working problems in class so that we can talk about it and talk about each one individually rather than me give a long lecture in this video format. I would rather spend more time working the problems. So this video is mostly to introduce terminology with practice problems coming in class. So name an alkane given its structure and draw an alkane given its name. There are steps that we follow in naming an alkane. Step number one is to name the main chain. You are going to take and find the longest continuous chain of carbon atoms and name the chain according to the number of those carbon atoms in that chain. We will primarily, well, no, not primarily. We will keep the main chain to be from one carbon atom, which is methane, to 10 carbon atoms, which is decane. For a complete list of the alkanes that we will be using, look at table 12.2 in your textbook, or you can study the alkane Quizlet. Once we find the main chain, we then number the carbon atoms in the main chain, beginning at the end nearest the first branch. From that point, we identify the branching substituents and number each according to its point of attachment on the main chain. The branching substituents, which I have alluded to their names, can be found on page 378 of chapter 12, and it is a figure 12.3. I have also created a substituent Quizlet for it to memorize the substituents. So thus far, we have identified the main chain and named it accordingly to the number of carbon atoms in that chain. We have numbered the carbon atoms in the main chain, beginning at the end nearest the first branch. We've identified the branching substituents and numbered each according to its point of attachment on the main chain. Now what we're going to do is we're going to write it all as a single word. When writing it as a single word, we use a hyphen to separate the numbers from the different prefixes, and we use commas to separate numbers if necessary. Again, we're going to spend some time in class doing this because it is a foundational piece to several things that we have discussed. Number one, being able to name an alkane helps us to determine if we're talking about conformers or if we're talking about completely different structures. We will be using line structures and condensed formulas in order to draw an alkane based on the name. So we're going to be using the stuff that we've already used. Plus, I want to spend some time in class on this because it is a building block for the remainder of the organic section in our course. Now, before we move on, there are 4 substitution patterns that can occur on an alkane carbon. If you think about it, you have carbon, and carbon has 4 bonds. So each of those bond locations can result in a substitution. Now, we call it a primary carbon atom if there's only one other carbon attached to it, which we represent that as an R. So if there's only one other carbon group represented as an R, then it's considered to be a primary carbon atom. A secondary carbon atom will have 2 other carbons attached to it. And these carbons could be the same or they could be different. That's why we illustrate it as R and R prime, is so that if they're the same, fine. But if they're different carbon attachments, then we can indicate that by the prime. A tertiary carbon atom is going to be a carbon atom that has 3 carbons attached to it. Now, once you get to a tertiary carbon atom, again, notice that we've distinguished the different carbon groups as R, R prime, and R double prime. But once you get to a tertiary atom, what you're going to see is that the reactivity significantly decreases because you start getting what is called steric hindrance, which I'll define here in a moment. The last substitution pattern is what is considered to be a quaternary or quaternary carbon atom. A quaternary carbon atom is one where there are 4 carbon groups attached to that carbon atom, which you will notice are listed as R, R prime, R double prime, and R triple prime. Again, once you get to that tertiary, and well, with quaternary, there's not going to be a reaction. But once you get to that tertiary, we're going to find out that there's going to be less reactions that will occur simply due to the steric hindrance that happens. And what steric hindrance is, it's a slowing of a chemical reaction due to simply having bulk around the reaction site. Think about it. You have carbon and all these hydrogens attached to it. Well, if you have carbon and all these hydrogens attached to it, it's like adding a ball on top of that carbon atom. And if you add one ball, okay, that gets in the way a little bit. But if you add 3 balls around a quarter, in fact, let's think about it this way to help understand the steric hindrance. Let's take a coin. Now, this is your carbon atom. When you add a CH3 group, it's like adding 1 ball. Well, that's okay because I still have plenty of area where I can attack in order for a reaction to occur. Well, if we have that carbon atom, and we have 2 balls of CH3 groups, We have just reduced the amount of surface area where this attack can occur. So, as you can imagine, if you have your carbon and you have four balls around it, there's no place for attack. And so the reactivity is going to decrease due to this steric hindrance.